The James Webb Space Telescope has always been an object of fascination for astronomers and space enthusiasts alike. It's a prominent achievement in our exploration of the cosmos, a telescope massive and sophisticated enough that its beautiful and eerie details of distant worlds are revolutionizing our understanding of the universe. Mankind launched this incredible observatory less than 5 years ago, but to this day, there's still so much we're learning from it, as exploring any place outside of our solar system is always incredibly challenging and filled with surprises. While space seems like a very different place from Earth, there's one thing that excites scientists about future explorations. There is increasing evidence of something unexpected on Proxima B, but the signals from Proxima B are mysterious. They do not always show up where we expect them, and by all accounts, they shouldn't be where we find them. Its mysteries are ones that the scientific community around the world is desperate to crack, because these signals might unlock the key to understanding if we are alone in the universe. Whoever solves it first will reap significant benefits in our understanding of potentially habitable exoplanets. What are these signals from Proxima B? How do we know they're there? And how close are we to overcoming space's greatest challenges? To understand them, I'm Alex McColgan and you are watching Astrum. Join with me today as we follow the progress numerous scientists around the world have made in interpreting what could be the most terrifying discovery from our nearest neighboring star system. Scientists did not always have the technology to study Proxima B in detail. Proxima Centauri b was an ambitious target for astronomers when it was discovered in 2016. It's located in the habitable zone of our nearest neighboring star, just 4.2 light-years away, practically in our cosmic backyard. What made Proxima B particularly interesting was its position in the Goldilocks zone, not too hot, not too cold, but potentially just right for liquid water to exist on its surface. Of greatest surprise to scientists was the detection of certain atmospheric markers within the initial spectroscopic data. Around 0.1% of the readings showed what could be interpreted as artificial compounds, and researchers found that the concentration of these markers increased with certain orbital phases. However, like the very trace amounts of unusual readings detected during earlier exoplanet studies, for example with TRAPPIST-1, this was assumed to be contamination or instrumental error. The question of whether there could be something unusual about Proxima B remained unanswered. In 2022, the James Webb Space Telescope began operations, showing unprecedented detail of celestial objects that previous telescopes couldn't achieve. As a result of this, there was a lot of excitement in the scientific community about whether there could be more information to glean about Proxima B, protected from the harsh rays of its volatile red dwarf star, where the temperatures would fluctuate between extremes we can barely imagine. Any potential biosignatures at this distance would be tremendously difficult to detect, but if any telescope could do it, it would be the James Webb. Excited by the possibilities, a team of international astronomers requested observation time, specifically to hunt for clues about Proxima B's atmosphere. While it didn't give us any conclusive answers to the mystery, it certainly added to the intrigue. The JWST detected unusual energy emissions from the planet using spectroscopy. Data from these observations suggested that there could be somewhere between 10 to 300 different molecular compounds in Proxima B's atmosphere, many of which shouldn't naturally occur together. But unusual spectroscopic patterns do not necessarily mean the presence of artificial structures. It could also be natural phenomena we don't yet understand. The mystery deepened. A follow-up study was conducted using multiple instruments on the JWST, with scientists hoping the combined data would paint a clearer picture of what was happening on this distant world. Unfortunately, initial results were inconclusive. The observations seemed contradictory at times. The mystery continued. The MIRI instrument on board JWST was particularly crucial for the next phase of study, and its mission was to take high-resolution, mid-infrared readings of the planet as it transited its star. But it also wasn't able to detect any clear signs of the origin of these unusual energy patterns around Proxima B. So after 18 months of careful observation, scientists prepared a comprehensive analysis, hoping that this time it would provide enough data for Earth-based supercomputers to work with. But again, no definitive evidence for the source was found. In 2024, another team of researchers proposed a new approach. Instead of relying solely on passive observations, they suggested using the JWST's capabilities in a different way. They were looking not just at the regular spectrum, but at irregular fluctuations that might indicate something entirely unexpected. Scientists believed that periodic patterns might be detectable if they examined the data from multiple angles. The new observational strategy was implemented, and after months of collecting data, the JWST sent back something that sent shockwaves through the scientific community. As the data was processed, they discovered something that defied conventional explanation: regular, patterned energy pulses that cycled at precise intervals. These were not random natural phenomena. They displayed the hallmarks of artificial origin. The pulses followed mathematical sequences that couldn't be explained by any known natural process. As it descended deeper into the data analysis, the eye pattern became clearer, and within that data was an answer scientists had been looking for all these years: a confirmation of non-random signals. And a few months later, a different research team using machine learning algorithms to examine the JWST data also detected the presence of these patterns from Proxima B. But NASA wanted more proof. They coordinated a multi-telescope observation campaign involving not just JWST, but also ground-based observatories around the world. This comprehensive approach was a simple yet very clever design. In an unusual move, the observations were conducted continuously for a full month, creating the longest continuous dataset ever collected for an exoplanet. Upon reaching certain conclusions, the data was released to the wider scientific community for peer review. This approach was similar to how discoveries of gravitational waves and black hole images were verified, by having multiple independent teams analyze the same data to ensure the findings were reproducible. As the analysis continued, the evidence only grew stronger, and unlike previous cases, the signal patterns became more defined with additional observation. The data sent back from this coordinated effort showed that the signals from Proxima B contained complex patterns that some researchers controversially compared to encrypted data packets. The repeating sequences contained what mathematicians identified as prime number relationships and mathematical constants that are universal across the cosmos. This combination of signals produced a large body of evidence that the international team of scientists was left to study. The results heavily suggested that these patterns couldn't be produced by any known natural phenomenon. Nowadays, most experts agree that what we're detecting is either an entirely new class of astrophysical phenomena we've never encountered before, or evidence of a technological civilization on Proxima B. That's a terrifying prospect. But how could such signals be coming from Proxima B, particularly with such regularity? Wouldn't such a civilization have attempted more direct contact, especially since they're in our cosmic neighborhood? NASA's JWST team recorded signal variations corresponding precisely with Proxima B's orbit around its star. However, the key insight came when they realized the signals were strongest when the planet was at a specific point in its orbit, direct alignment with both its star and our solar system. This peculiar timing suggests the signals might be directional, perhaps deliberately aimed toward our region of space. These precisely timed emissions might still be a problem for Earth-based astronomers if it wasn't for an interesting feature of the James Webb Telescope's position. The JWST operates at the second Lagrange point, L2, a gravitationally stable location 1.5 million kilometers from Earth. It is believed that this position gives the telescope a unique vantage point, possibly allowing it to detect signals that ground-based telescopes might miss. Because of the telescope's location, some of these signals can be observed without interference from Earth's atmosphere, thus explaining why JWST's findings seem more definitive than previous observations. LRO further illuminated our understanding of the Proxima B situation. It was once thought that the signals would be consistent and unchanging if artificial. However, as JWST continued its observation campaign, it began to notice something unexpected. The signal patterns appeared to be evolving over time, becoming more complex and structured with each observation window. It turns out the signals aren't static but seem to be adapting, almost as if responding to being observed. This evolution was even observed to move in a sort of cycle, both by intensity and by complexity. Around the midpoint of Proxima B's 11.2-day orbit, when the planet was at its greatest elongation from our perspective, the signals seemed to diminish, but then would return with greater complexity as the planet approached inferior conjunction. So, something or someone is either generating these signals, or something must be transmitting them toward us. There are several hypotheses as to why this might be happening. A technological civilization on Proxima B, aware of our solar system's potential for life, could be attempting contact using a method they believe would be detectable across interstellar distances. Another possibility is that what we're detecting is a two-step process whereby an automated beacon is operating, perhaps left by a civilization that has since disappeared or evolved beyond our recognition. It could then be programmed to increase in complexity once it detects observation, like a cosmic version of the Turing test to determine if another intelligence is listening. It could also be that what we're detecting isn't meant for us at all, but is instead some form of local communication or energy infrastructure that we're inadvertently intercepting. But what makes the discovery truly terrifying to some scientists is the nature of the mathematical patterns themselves. They contain elements that suggest knowledge of physics beyond our current understanding. But JWST's observations mean that our understanding of potential extraterrestrial intelligence suddenly seems much more concrete. If these signals could be fully decoded, you would not need to speculate about the existence of other technological civilizations, which is convenient, because the implications of this discovery are far more profound than we at first thought. James Webb has very sensitive instruments, far more advanced than anything we've previously sent into space. This means that at the poles of its orbit, there exist opportunities to gather data that are never available to Earth-based telescopes. No matter what time of day or year, the Earth's atmosphere never interferes with JWST's observations at L2. Naturally, a telescope that never has to contend with atmospheric distortion is bound to see things more clearly. However, scientists were not prepared for exactly how clear the Proxima B signals would turn out to be. For context, detecting any kind of atmospheric composition on an exoplanet is extraordinarily difficult. Previous telescopes could barely confirm the existence of atmospheres at all, let alone analyze their components in detail. JWST houses a suite of instruments specifically designed for this purpose, which uses specialized sensors to measure chemical compositions. With it, JWST found patterns that had mathematical properties comparable to prime number sequences, the Fibonacci series, and even representations of constants like pi. This makes it the most compelling evidence of a non-human origin for any signal ever detected, making it potentially the coldest observation for humanity's sense of cosmic uniqueness. That's more paradigm-shifting than any previous discovery in the search for extraterrestrial intelligence. The crater-like features on Proxima B shielding portions of its surface from its star's harsh radiation might have created the perfect location for housing a technological civilization, but other more interesting, useful information could be found within these signals too. Mathematical proofs, technological concepts, or even philosophical ideas, perhaps. It didn't stop there. The JWST's NIR spec instrument discovered regular variations in the signals that strongly correlate with mathematical constants. Its data confirmed that the patterns on Proxima B may not be just limited to simple repeating sequences, but may be distributed across multiple layers of complexity. NIR spec found that the signal structures contain what mathematicians call nested patterns, patterns within patterns that suggest a hierarchical organization of information. To put that into perspective, human communication contains maybe 3 to 4 layers of such nested complexity. The signals from Proxima B show evidence of 7 to 9 layers, suggesting a system of communication or data organization far more sophisticated than anything humans have developed. So yes, that is an astonishingly complex finding, and it might not be easy to interpret, but it helps us in learning about the potential for other intelligences and how they might think and communicate. What makes the discovery particularly unsettling is the rate at which the signals are evolving, becoming more complex with each observation cycle, as if whatever is generating them is learning or adapting to being observed. The implications of this discovery could help make space exploration more focused and purposeful in the coming decades. It could be used to guide the development of future telescopes and observation technologies. It could also be used to help formulate protocols for potential contact scenarios. But the biggest and most immediate application for this discovery is in driving a new field of xenomathematics, the study of how non-human intelligences might approach logical and mathematical concepts. After all, mathematics is often considered a universal language. You see, getting a genuine signal from another civilization would be a profound moment in human history. And the deeper into the implications you delve, the more questions arise, and the more philosophically challenging it becomes. Having to confront the reality of another technological species heavily impacts our understanding of our place in the cosmos. But the signals from Proxima B have 1/6 of the complexity of our most sophisticated encrypted communications. So if we are able to successfully decode even a portion of these transmissions, it's likely they contain information that could revolutionize our scientific understanding. China, in collaboration with Russia and other countries, is planning to build a dedicated array of radio telescopes by 2029 that will be targeting the Proxima Centauri system, where they plan to establish continuous monitoring. The U.S. also plans to have its deep space network reconfigured by 2030 to better detect and analyze similar signals. They plan on launching their first specialized SETI spacecraft, followed by a more advanced detector satellite, and finally building a dedicated exoplanet communication research center, which will happen no earlier than 2027, and that may be our first coordinated global effort to respond to potential extraterrestrial signals. All in all, in the field of astrobiology, interest is skyrocketing. While I'm being a little tongue-in-cheek when I say that, it is evident that interest in potential extraterrestrial intelligence as a serious scientific endeavor is increasing. Before the JWST discoveries, the number of peer-reviewed papers published annually on the subject had risen to about 50. America, Russia, China, Europe, Japan, and India have all initiated new research programs focused on signal detection and analysis. As more countries and research institutions set their sights on this mystery, it may make you wonder, what's the end goal? Do we simply want to confirm we're not alone, exploring the cosmos for the betterment of humanity? Or do people sense existential implications in these discoveries? While researching this video, I found out a lot of eye-opening perspectives on why detecting intelligent signals from space and especially from our nearest stellar neighbor, might well be something we approach with both excitement and caution in the coming decades. The first concern relates to what scientists call the Great Filter hypothesis. You may have heard of the Great Filter in discussions about the Fermi paradox, as theories suggest it explains why we haven't detected abundant evidence of intelligent life despite the vastness of the universe. The terrifying implication is that if we detect a relatively young civilization like our own, it might mean the filter lies ahead of us, not behind us. In other words, something might cause technological civilizations to disappear shortly after they reach our current stage of development. However, it's not all doom and gloom. The signals from Proxima B aren't any more threatening than a distant lighthouse is to someone observing from shore. They appear to be regular broadcasts rather than directed communication, or, worse still, evidence of expansion toward our solar system. A lot of the time, that's not something to fear. We can also produce scientific models of Proxima B as a byproduct of studying these signals. Assuming we don't want more tritium in the world, it means we need to find another approach to understanding these transmissions, especially if technology improves enough for more direct observation to become a reality. Fortunately, we have a world in orbit around Earth right now, which has been outfitted with the most sensitive instruments humanity has ever created, thanks to the James Webb Space Telescope. Earth's scientific community currently has the telescope scheduled for additional observations of Proxima B over the coming year. We aren't talking huge quantities of data yet, but because it is all being openly shared among the scientific community, not just in tiny research groups, it can be collectively analyzed. This makes mapping Proxima B's surface and finding the sources of these signals all the more vital. If we intend to understand potential extraterrestrial intelligence, interpreting these patterns will be incredibly important. However, collecting and analyzing this information might be more challenging than you'd think. And I don't just mean the vast distances involved. There are bigger problems we'd have to face if we want to establish any kind of meaningful communication. One of them is time. Because of the 4.2 light-year distance, any signal we detect left Proxima B over 4 years ago, and any response we might send wouldn't arrive for another 4 years. This means an 8-year round trip for a simple hello and response. The Moon has no atmosphere to interfere with observations, so perhaps establishing a lunar observatory specifically designed to monitor Proxima B could be advantageous. Once there, the precision instruments could potentially reveal more detail about the source of these signals. Lunar observatories would allow astronomers to stay safe inside bases, while the automated telescopes do the observation work in the harsh lunar environment. It's exciting to see different approaches being taken in the mission to understand these signals, but while there are successes, there are also limitations. In late 2024, NASA announced that it was considering a dedicated probe to the Proxima Centauri system, which had been intended to be the first-ever direct mission to a neighboring star. The mission was initially intended for launch in the 2040s, but due to the new findings and a renewed interest in interstellar exploration, some are pushing to accelerate development. The probe, still in conceptual stages, would take decades to reach its destination, but could provide our first close-up. Look at this intriguing planetary system. This is a challenging prospect, as no human-made object has yet traveled beyond our solar system with the specific intent of reaching another star. NASA is not the only space agency finding interstellar exploration challenging. The distances involved make this perhaps humanity's greatest technical challenge. But even with our current technology, we continue to gather more data from the James Webb Space Telescope, and perhaps they would have been surprised anyway, as it turns out the signals from Proxima B, that potentially paradigm-shifting discovery about our cosmic neighborhood, are proving oddly difficult to interpret fully. We have repeatedly detected them in careful observations, And yet, when we take a closer look at what they might mean, instead, a mystery appears. The established belief among scientists today is that we need to approach this discovery with both rigorous skepticism and open-minded inquiry. But because it's so complex to analyze these patterns, it's difficult to know for sure exactly what we're detecting. It would be unfortunate to misinterpret natural phenomena as artificial signals, or equally unfortunate to dismiss genuine contact from another civilization. Sadly, even the JWST, the most powerful space telescope humans have ever built, has its limitations. Its onboard instruments cannot definitively prove the origin of these signals. But there is a new radio telescope, array being built that might. The reason why I said earlier that 6 countries had sent major research teams to work on this problem is that several others have joined the effort recently. As of early 2025, independent research teams from Brazil, South Korea, and Australia have also begun dedicated observation campaigns. And their discoveries provided even more pieces to this cosmic puzzle, as well as raising further questions. NASA has actually been working closely with international partners on this effort, providing them with scientific expertise and data-sharing protocols in a spirit of mutual international scientific collaboration. If these findings are confirmed, they could represent the most significant discovery in human history. Evidence that we are not alone in the universe. This could fundamentally alter our perspective on our place in the cosmos, and perhaps even provide insights into our own future as a technological species. Whatever the source of these signals ultimately proves to be, one thing is certain. The mystery of Proxima B has captured the imagination of scientists and the public alike, and the search for answers continues.